Swayam Prabha. Digital India. Educated India.
Hello, welcome to Module 6, Week 1 of our course on Introduction to Dynamical Models in Biology. In the last module, we have learned the basic concepts of numerical solution of ordinary differential equation. We have learned how to use Euler's method. We have learned the basic concepts of Euler's method. Now, we will learn in this module better algorithms to implement numerical solution of ordinary differential equation. Now let us look back into Euler's method to understand why we want to know better algorithm. In Euler's method, what you are doing, suppose your function for x is this one, the solid line shown here in the graph. T is varying in this horizontal axis, x is varying on the vertical axis. At time t, value of x is this one, the yellow point. At time t plus delta t, if you increase delta t by time by delta t, the real value, the exact value along this function for x will be this green one, that is x at t plus delta t. In Euler's method, what you are doing, you are estimating the value of x at t plus delta t using this relationship. X at t plus delta t is equal to x at time t plus delta t into function of x and t. Where you have got this function? You have got this function from the differential equation. Now in other words, what you are doing here is that x at t plus delta t is equal to x at time t plus delta t and slope. Because remember, the derivative of a function at a particular point is nothing but slope at that point. So at time t, x is this yellow point. And if I draw a slope or a tangent along this line, that is the curved line which is a function for x, and if I draw a tangent here, the slope of that tangent will be dx dt. So what we are doing, we are getting the value of x at a next time point, that is at t plus delta t, by doing linear extrapolation along this tangent. Along this tangent you are doing linear extrapolation and you are getting the value of x at this new time point as shown in by the pink dot. Now as we can see, obviously as we are following this tangent, we are following this slope, we are getting a value slightly higher than the real value of x, which is shown by green. So you can see there is a difference between the pink dot and the green dot. This error is coming because from the yellow point you are doing linear extrapolation along the tangent having a slope dx dt. We can rectify this one if I correct my estimate of slope slightly and generate another line here having a different slope. And if I follow this line, most probably I will reach at the right value at the green point. So today in this module, we will study an algorithm which replaces this estimate of slope by a better estimate of slope, or rather an average estimate of slope, which is much better in extrapolation and getting the value, new value of x at time t plus delta t. This method is in general known as Runge-Kutta method, and there are multiple algorithms belonging to this family. What we will discuss here is called fourth order Runge-Kutta method. So we will discuss about this algorithm, and we have to remember that there are many modern versions of this algorithm available having different advantages. And most of the time people use various versions of this algorithm in different form for solving ordinary differential equation. So let us start. I have a function ODE dx dt which is equal to f xt. in my earlier example, actually fxt, when I was discussing about the spread of infectious disease, fxt was equal to r into 1 minus x into x. So I am writing in a generalized form here, because we will try to derive the understand the method in a generalized fashion. So dx dt is equal to a something which is a function of x and time t. So k1, as in Euler method, k1, the slope is equal to the first slope, k1 is equal to dx dt, which is equal to this function f of xt. So if I look graphically, what I have, in this horizontal axis I have time, in this vertical axis we have x, and this curve is nothing but my function of time representing x. X is equal to function of time. So I am at time t. This yellow dot is the value of x here at time t. So it is xt. Now if I draw a tangent here with a slope which is equal to dx dt as given there, I will have this bluish line, and if I take a time step at t plus delta t time step, and draw a vertical line as shown in this dotted line, this dotted line intersects with this blue line at this red point. So this is my estimate by Euler's method for the value of x at t plus delta t. And obviously you can see it is quite different from the real value here. So it is a lesser estimate. Now what if I do some modification? What I do, I extend this tangent at this yellow point along with a slope k1 up to the midpoint, that is up to t plus delta t by 2. So this is halfway delta t by 2. So if I draw a vertical line at t plus delta t by 2, that is the dotted line shown here, that intersects this blue line at this orange dot. So this position it intersects. What is the value of x here? The value of x at this position is x plus k1 into the interval delta t by 2. So the value of x here in this orange is actually x plus k in k1 into delta t by 2. So now what I will do, I will estimate the slope. If I draw a tangent there, and if I estimate the slope of that, I will get the slope k2. So using this differential equation dx dt, I calculate the slope of this orange line drawn at this orange dot. That will be equal to k2 equal to dx dt equal to function of x plus k1 into delta t by 2 and t plus delta t by 2, because these positions coordinates are t plus delta t by 2 and x plus k1 into delta t by 2. So I get the slope here at this orange point. Once I have got the slope here at this orange point, I draw a line at this original yellow point using that same slope. So I get a orange line here. I will clean this part so that things become clear for you. So I am taking this orange line slope k2 and drawing an orange line at the original position of x at this yellow point. So I get this new orange line, and I extend that new orange line till it intersects the vertical line drawn at t plus delta t by 2, that is this vertical line. So I get a pink dot here. This is the point of intersection. What will the value of x that there? The value of x there would be, value of x at that pink point will be x plus k2 into delta t by 2. That will be the value of x. So now if I draw a tangent having a slope, or a line having a slope dx dt, the slope of that line will be k3 equal to dx dt equal to f function of x plus k2 delta t by 2, that is the value of x at that position, and the value of time at that pink position, that is t plus delta t by 2. So in this way, what I have got the slope of this pink line, which is k3. So now let us clean a bit and see what I will do next. Now take that slope k3 and draw a line at this yellow original point where x was, for having the same slope as k3. So I get this new pink line. So I have a new pink line drawn at the original value point position of x and extend it till it intersects the vertical line drawn at t plus delta t. That is the time step we are taking. So that intersection point is this black dot. What will be the value of x there? The value of x there in that black dot will be x, the original value of x, plus k3 into delta t. So you have taken the slope of k3 and had extended it up to by an increment delta t. So the new value of x at this black point is x plus k3 plus delta t. Now at this black point, I draw a black line having a slope dx dt. So the slope of that line will be k4, which is equal to dx dt at that point. At that point, the dx dt will be function of x plus k3 delta t plus and t plus delta t. So the coordinates here, the t is t plus delta t and x is x plus k3 delta t. So I can calculate the slope at that point. So what I have now is three slopes: original k1, k2, k3 and k4. So what I do, I take an average of these four slopes, k1, k2, k3 and k4, and I take a weighted average. That means I give different weights to each of these slopes. For k1 and k4 we give equal weightage, but for k2 and k3 I give twice the weightage. So I get the mean value of k is k1 plus 2k2 plus 2k3 plus k4 divided by 6, because remember 1 plus 2 plus 2 plus 1 is equal to 6. So if I now draw a line having mean k slope along this initial position of x, that is this yellow point, then I get this green line. So what I have done, if I clean a bit, so what I have done, I have three slopes, k1, k2, k3 and k4. I have taken a weighted average of all these four slopes and got a new slope k mean, and I have drawn a line, the green line shown in this graph, which has a slope of mean k and goes through the initial position of x at time t. As you can see, if I extrapolate this line at t plus delta t time, it will reach the green point, and the green point is on this original black curve, which represent function of time, or the represent the behavior of x with respect to time. So in this way we have extrapolated using an average value of the slope and got the new value of x at t plus delta t time after the increment of time by delta t. So if I brief what we are doing here, you have an ordinary differential equation given first, which is the generalized form I have written, dx dt is a function of x and t. I calculate first the first slope k1 using the same Euler's method, which is nothing which I have used in Euler's method. K1 is dx dt, which is a function of x and t. Then using that slope I calculate a new slope k2, which is nothing but function of x plus k1 delta t by 2, that is the halfway of your increment, and t plus delta t by 2. That way I use k2 to calculate the k3, and then I use K3 to calculate K4, 4 slopes. Then I make a weighted average of these 4 slopes K1, K2, K3 and K4 to get a mean value of K, that is K bar. In general, what we know, as we have learned in case of Euler's method, x at a new time point, that is x at t plus delta t, is equal to x at the older time point, that is x at time t, plus the increment in time delta t into slope. Here we will use the average slope k bar. So if x at time t was xt, this one, then x at time t plus delta t would be x at time t plus delta t time, that is the increment in time, into the average time, average slope. Here we should have 1 by 6, which was missing initially. So this way, using this average slope, this is the average slope, I can calculate the new value of x. Let us try this method. This is the 4th order Ranjikuta method on our problem of spread of infectious diseases. So if you remember, the ordinary differential equation for modeling this spread of infectious disease was dx dt equal to r into 1 minus x into x. R is given as 0.1, 0.5, x at t equal to 0 is 0.02, and I am taking here delta t as 1. So I will increment time by 1. So how will proceed? First I will calculate k1. So consider I am at time point 0, t equal to 0. So the value of x will be 0.02 as given. This is the initial condition. So at this point the slope k1 will be equal to dx dt into r into 1 minus x into x, which is equal to 0.5 into 1 minus 0.02 into 0.02, which is equal to 0.0098. So in this table I have written it here, 0.0098. Now I have to calculate, I have to draw a line at this value of x and t having a slope k1, and that I will extend up to delta t by 2 time. So the new value of x there will be x at delta t by 2, that is x, remember delta t is 1, so x at 1 by 2 is equal to x at 0 plus k1 into delta t by 2. So that is at x at 0 time point is 0.02, it is already given here, plus the slope I have calculated, so this slope comes here, into 1 by 2. 1 is delta t, that is in by 2. That gives me a value 0.0249. So I got a point from delta t by 2 away from time equal to 0, and the value of x I have calculated at that point, that is this one. I want to draw a line there having a slope equal to dx dt, and the slope there will be k2. Dx dt is equal to r into 1 minus x into x. So let us put the numerical value. R is 0.5, 1 minus x, x is this new value of x into, so this one, this equal to 0.01214. So I write down it here in this table. In this way, I again try to calculate k3. So to calculate k3, what I will do? Using the slope k2, I will draw a line from the position of x at t equal to 0 and extend it so that it reaches up to t by 2, delta t by 2. So the value of x at that position would be x at delta t by 2 will be equal to x at 1 by 2, 1 is the delta t, will be x, value of x at 0 time point plus k2, because now I will use the slope k2 into delta t by 2, and if you put this value, so k2 is this one that I have calculated in the last step, I get a new value of x as 0.02607. So using this value, I will calculate the slope of a line drawn having a slope dx dt. So the numerical value of the slope will be k3, which is the new slope, is equal to dx dt is equal to r into 1 minus x into x. R is 0.5, 1 minus x, x I have calculated just now. These two values are for x, 0.02607. So if you multiply that, you get 0.012695. So I put that value here. So I have got the value of k1, k2, k3. Now I have to estimate the value of k4 using the value of k3. So using the value of k3, I draw a line at x t equal to 0 and extrapolate it up to t, delta t times 10. So the value of x would be x at delta t, that is x at 1 equal to x at 0 plus k3 into delta t. So if I put numerical values, x at 0 is 0.02, that is the initial condition, plus the value of slope that I have calculated in the last step into 1 is the time step size, is equal to 0.032695. So that is the value of x when I extrapolate the straight line having slope k3 from x equal to 0. So it's x at 0. Now let us calculate k4. So if I draw a line having slope dx dt at that point, the slope of that line will be k4 equal to dx dt equal to r into 1 minus x into x. R is 0.5, x is 1 minus 0.032695 that I have calculated just now. So these two values are here. If you multiply, you get a value of k4 as 0.015813. So what I have got k1, k2, k3, k4. So now I take a weighted average. So remember, we are giving different weightage to different slopes. So for k2 and k3, the weightage is 2, 2. For rest of k1 and k4, the weightage is 1. So the total weightage is 6. So we have to sum k1 plus 2k2 plus 2k3 plus k4 divided by 6. We have already calculated the value of k1, k2, k3 and k4. You put those numerical values here. Don't forget to multiply by 2 for k2 and k3 and you get a mean value of slope as 0.01257. So I write it down in this table. So if I now increment time by delta t using this mean slope, I will get a new value of x at t plus delta t. So t was 0, initial time is 0. So value of x at, this is essentially x 0 plus delta t, that is x at delta t is equal to x at 0 plus 1. Remember, x delta t is 1. That will be equal to x at 0 time point plus mean k, mean slope into delta t. X at 0 time point is 0.02. The mean slope is 0.012547. I have calculated it here into the time step 0.1. So I get a new value of x, that is 0.03257. So in the table I write at time 1 the value of x is 0.023547. I have written it here also, the same thing. So if I see this method, now I have moved from time 0 to time 1 by increment of delta t equal to 1 using the mean k. Now I am at x t at t equal to 1. I can again calculate k1, k2, k3, k4 using the same method and can calculate the weighted average of these four. And I have done that and shown in the table, that is 0.01997. Now using the same addition, that this mean into delta t, that is x at time 1 plus delta t will be equal to x at time 1 plus k mean into delta t. So this is nothing but x1 plus 1, that is x at time point 2 will be x as 1 plus k is 0.019997 into delta t is 1. X at 1 is this value 0.032547. So if you sum up, you get the value of x at 2, that is this value 0.052545. So in this way you can keep on calculating these 4 slopes at each of these x as you are increasing time by delta t, and can calculate the value of x at the next time point. That was I have shown briefly in this table, and you stop at the final time point. For example, the time point may be 20 and you get the value of x at time point 20. So this is in brief fourth order Runge-Kutta method. There is exhaustive mathematical explanation behind this. We have avoided that and tried to intuitively and graphically understand how this algorithm works. Now let us look that by doing this complicated calculation of average k, are we gaining something? What I have done in this slide, I have compared the Euler's method with this fourth order Runge-Kutta method. Both are numerical method, and try to understand what is the difference in result we obtain for the same system using these two algorithms. So our ODE is the same one that we use for modeling spread of infectious disease, that is dx dt equal to r into 1 minus x into x. X at time 0 is x naught, that is equal to 0.02, and r is 0.5 as we have kept earlier. So the first graph here that I have shown is the result from Euler's method. You have seen this graph earlier. The gray line is the exact analytical method, result from the exact analytical method. The dotted line shown here is the result from Euler's method when you use delta t equal to 0.1. It matches almost with the analytical method or the symbolic method. But the problem starts when you take a bigger delta t equal to 1. Then the result is this black line. As you can see, and you have noticed earlier also, that it is deviating from the real original result. That is the result obtained by analytical method. That means this approximate method has error when I increase delta t to 1. Now let us look what we get when you use the Runge-Kutta method that we have discussed till now. So again, this plot 2 is the same system. Again, I have plotted the exact solution by gray line, and I have done 2 simulations using the Runge-Kutta algorithm with delta t equal to 1 and delta t equal to 0.1. You can see clearly in this graph, all these 3 have the same data and they have got collapsed in the same line, and you cannot see them because they are overlapped. So it shows that in the Runge-Kutta method we have used a average slope. This average slope technique is giving us better result, more accurate result than the Euler's method. As I have said earlier, most of the recent versions of the algorithm that's widely utilized for solving ordinary differential equation in biology and other fields are actually derivatives of the fourth order Runge-Kutta method, or in general we say it belong to the same family. Now what I have discussed till now is that if I take an average slope at a particular time point and then estimate the new time value of x at the new time point, we are getting a better result. But still the issue of delta t lingers here. If you remember, in our previous module we have discussed that if your delta t is bigger, your error will increase. And even if you use Runge-Kutta method, there will be situation where delta t, if you take a bigger delta t, you will have huge errors in your calculations. So how to decide what delta t value we will take? If you remember, if I use very large delta t, I will have erroneous result. If I use very small delta t, using the algorithm or Runge-Kutta method also, I will get a very good result and the error will be less. But the problem is your computation time will increase. Now, there is another issue. In this whole algorithm, whether it is the Euler's method or the Runge-Kutta method, if you have noticed, I have used a fixed value of delta t for my whole calculation. But look at this graph shown in this slide. The same plot for the spread of infectious disease model that we have. So you have time in the horizontal, x is in the vertical axis, and this solid black line is the function of time. X is a function of time. Now, as you can see, in the lower part, when time is less, lower value, if I take, you can intuitively understand, if I take a large delta t, my error will not be so significant because the line is almost flat, almost linear. The similar thing at the end. Here also the system is almost linear, almost horizontal. So if I take a delta t large, I will not have much problem. Whereas in this middle region, when x is changing drastically, very fast with respect to time, I have to take small interval of delta t so that I get less error in estimate. That means just looking at this graph, I can easily say that it is not wiser to use the same delta t for the whole calculation. Maybe where x is not changing much with time, I can use a large delta t and reduce time of computation. And then where in the region of the function where x is changing very fast with respect to time, I use small delta t increment so that I get less error. That means I have to adapt my delta t along my solution. As I am solving this ODE, I should keep on changing or adapting delta t based on the need, based on the function. So that's what we call adaptive time step size algorithm. So what we will do in these adaptive algorithms, we will try to estimate the optimum delta t as we keep on solving a particular ordinary differential equation. There are many ways of doing this one. I will discuss one generic method which has been implemented in many algorithms with various variations. To use an adaptive method, what I require is that I have to take a delta t and then I have to estimate how much error is there in my calculation if I take that delta t. For example, suppose you are at time equal to 0 and you want to move forward and you have taken delta t as 1. So you have to estimate there that if I take delta t equal to 1, how much error do I get? Is the error very high? If the error is very high, I will reduce delta t maybe to 0.5 and try again. So I want to continuously calculate error in my estimate and change the value of delta t as I solve the ODE. Now if I have to estimate error, I should know what is the real value. That means I should know what is the real function of x with respect to time. Now the problem is, if I know the real function, then I don't need to solve it. And as we have discussed, analytical solution of most of the ODE is very difficult in most of the cases. So actually, I do not know the real value of x at a particular time point as per the real function, as I don't know the real function. Then how can I estimate error? There is a way out, and that way out I will discuss now. Rather than comparing with the best one, with the real one with your algorithm, you take two algorithms. One algorithm more accurate than the other one, and you know that. So maybe there are many algorithms in the family of Runge-Kutta method. We have discussed about fourth order. There are 5 order method of Runge-Kutta algorithm also, and that one is better than the fourth order one. So we can take two different algorithms. One is better than the other one. So what you do, you calculate the new value of x at the next time point using these two methods and calculate the difference between these two methods, result between these two methods. So that difference in result obtained by these two methods is my estimate of error. So what I am doing? I have a ODE given to me. I take a delta t time, suppose that is equal to 1, and then I compute value of x at t plus delta t using method 1. So that may be fourth order Runge-Kutta method. And I call that result at x1. Then I do the same calculation to get the value of x at t plus delta t using a new method. This may be fifth order Runge-Kutta method, which is known to give more accurate than the fourth order Runge-Kutta method. And I calculate the value of x at t plus delta t. Let us call that x2. And now I calculate the difference between x2 and x1. That is my error. Error is the absolute value of difference between x2 and x1. So once I have calculated the error, now I do some test. As a user of this algorithm, I decide beforehand how much error I will tolerate. So I have decided a upper limit of tolerance and lower limit of tolerance. Suppose I can decide the error should not be bigger than 10 to the power minus 6 and it should be in the range of 10 to the power minus 8 to 10 to the power minus 6. So this is my tolerance limit. So what I do, I have computed the error, just I have said. Then I use a logic. If this error is bigger than the higher maximum value of tolerance, that means the error is bigger than the tolerance error I will accept, I reject the calculation. I say this delta t is not good enough, and I reduce delta t to half of it, delta t by 2, and I go back again to step 1 and do the whole computation by method 1 and method 2 and calculate the error again. And again I check whether the error that I am getting is bigger than the maximum tolerance value that I will allow or not. Suppose now the error is not bigger than the tolerance value that I will allow, the maximum tolerance value I will allow. Rather, otherwise, it is either smaller than that or equal to that. So, if that is true, that it is not bigger than the maximum tolerated value I will allow, then what I will do, I will accept that result obtained by the accurate method, that is the second method. So, otherwise, take result for the more accurate method, that is the method 2. Now, if the error is less than the tolerance value, that is the minimum value of tolerance that you will allow, what you do? You increase the time step, because you have realized that the delta t that you are using is giving you very accurate result. So why don't I increase delta t slightly and see whether that will still allow me to work in a reduced error way. So what you are doing here, you double the step size from delta t to t delta t and do the calculation for the next time point. Otherwise, you maintain that delta t as the same value. Now you move to the next time point and do the same calculation and use the same logic from 1, 2, 3, 4 and 5 and calculate the value of x. So what we are doing here is that depending upon the error, whether the error is big or whether the error is small, we are changing the value of delta t. Whether the error is big or small is decided by the user who decides the tolerance limit. So as I said, I can say I want the error to be between 10 to the minus 8 and 10 to the minus 6. So my tolerance limit maximum value is 10 to the minus 6, whereas the lower value of tolerance is 10 to the minus 8. In this way, I can use Runge-Kutta method, the same Runge-Kutta method, but with an adaptive time step, and obviously that will give me better result and faster simulation. Most of the algorithms that is now implemented in the ready-made softwares that people use, biologists use to model ODE-based problems, actually have this type of adaptive time step algorithms, and they are easily usable. So let us jot down the key point that we have learned in this module. We have discussed the basic features of fourth order Runge-Kutta method. Remember, there is an exhaustive mathematical explanation and derivation for this algorithm. We have avoided that. We have tried to understand it intuitively and graphically. And also remember, this is not the only algorithm available for as a Runge-Kutta algorithm. There is a family of algorithms which use the same idea of using average of multiple slopes calculated at a particular position. In comparison to Euler's method, in Euler's method you have only one slope that you used for calculating your next value of x at the next time point. This method, this family of algorithm based on Runge-Kutta method and others which are usually used with adaptive time step algorithm, so that the delta t, the time step, is not fixed. It keeps on varying depending upon where you are in the function. That's all for today. Thank you for listening.